non-inverting Schmitt trigger circuit. So far, whatever we have seen is the inverting Schmitt trigger circuit. And now we will try to see how exactly a non-inverting Schmitt trigger circuit can be realized, right? So now the nature of the waveform remains same. Only thing is that whenever the input crosses UTP, right? So your output should go from minus V naught set to plus V naught set, unlike what we have seen in the inverting configuration, right? So once the input goes below LTP, then your output will go from plus V naught set to minus V naught set. So that's what we are supposed to see as long as an inverting or non-inverting Schmitt trigger circuit is concerned. Let us try to take the circuit and please try to notice the changes what we are going to make here. So here I have one input resistance and I have got a feedback resistance, something like this. See here, this is connected to ground. This very much resembles what kind of circuit without any proper nomenclature here? You have to quickly recall what circuit it is. Does it not resemble your inverting amplifier? All of you are able to listen to me or not?
Yes, sir.
Yes. Does it not resemble your inverting amplifier?
Yes, sir.
Okay. But the only difference here is I am connecting the terminals in the different directions, right? So had it been minus here and plus here, it would have been an inverting amplifier. Now this is what is the difference, right? So a non-inverting Schmitt trigger is very similar to the inverting amplifier in the structure, but there are a lot of differences in the principle of working, right? So that's what you are supposed to understand. So here the output is fed back to input, but it is a positive feedback, right? So let me write this as V in here. Okay, so this I will write as VI, that is the voltage across the input resistance. So since this is the virtual ground here, right, I can definitely take the voltage here as V naught. This is how I draw the circuit diagram for a non-inverting Schmitt trigger circuit. So input given to non-inverting terminal, and the feedback is also given to non-inverting terminal. This is a very important thing. So this you must write whenever the explanation on non-inverting Schmitt trigger circuit is asked. Okay. So now let us try to see how does it work. Okay. Now let us say, now let me draw the the waveform here. Let me draw the waveform. I have the input waveform something like this, T. This is what is my V in here. Okay. So now as usual I have to derive UTP and LTP. So something like this I will draw for UTP, something like this I will draw for LTP. This is UTP, this is LTP. So what are the values of UTP and LTP? We will see as and when we analyze this particular circuit. Now here I have got the output T. Now see here, I take this UTP as the reference, and here I will take the LTP as a reference. So now here my output would become something like this. This you can compare in comparison with your inverting Schmitt trigger circuit. So I write it as V0, and this is plus V0 sat, this is minus V0 sat. If you want, you can, I just, for your understanding, I will continue it. So yeah, I can take it here. Up to here I will take. So this probably will give you the clear idea, because your pulse width in both the cycles are going to remain same as long as your UTP is equal to LTP. This is what is the circuit diagram, the waveform for this circuit. So probably you should be able to draw this, write this. All of you are taking down these things or not?
Yes, sir.
Okay. Now we will try to have the analysis. How would you get this kind of waveforms, right? Now let us start with the assumption. So the input voltage is at ground level, that is this one, the first point. Say V in is at ground level and your V0 is at minus V0 set. So V0 is at minus V0 set. So if that is the case, so what will be the voltage across, I just take it above this, okay, something like this. So what will be the voltage across R1? In this case, what will be the voltage across R1? So VR1 I will write the voltage across R1, VR1, which I have also written as VI here. That is insignificant. You can write it as VR1 only. So this you can write it as VR1 only. So this VR1 is the output voltage into resistance of the same branch divided by total resistance. This is a very well known parameter to us, right? So this is minus V0 sat into R1 divided by R1 plus R2. So this is what is the voltage across R1, VR1, when your output is at minus V0 set. All of you agree with me or not?
Yes, sir.
Okay. So now this is negative. This is very important because it is minus V0 set into R1 divided by R1 plus R2, right? So now VR1 is negative. The non-inverting terminal will be on the negative side only, because this VR1 is this voltage. So now the non-inverting terminal will be on the negative side since VR1 is negative. So therefore this implies the non-inverting terminal is at negative potential. The non-inverting terminal is at negative potential. So obviously once the non-inverting terminal is at the negative potential, right? So the inverting terminal is grounded, non-inverting terminal is at negative potential. Obviously, your output has to remain at minus V naught sat only, correct or not? So therefore, it makes the output to remain at minus V naught sat only. The output will remain at minus V naught sat only. We had started from here. Okay. The output will remain at minus V naught sat only. Now, if at all you want to cause or you want to make the output to switch from minus V naught sat to plus V naught sat, right? If the output is to switch from if the output is to switch from minus V naught sat to plus V naught sat, if the output is to switch from minus V naught sat to plus V naught sat, so what should happen now? What should be the condition? The input voltage must raise above the UTP, right? V in should be greater than, say, voltage across R1. Your input voltage should be greater than the voltage across R1 because the voltage across the R1 is negative, right? So your V in should be greater than VR1, or you can write it as if V in is equal to or greater than the magnitude of VR1, then your V naught will now switch to plus V naught sat. V naught will now switch to plus V naught sat. So this action takes place. This action takes place. So you can see here, I'll just bring it down, right? Once your input is above the UTP is nothing but your voltage here, that is VR1. So the output is changed from minus V naught sat to plus V naught sat. Okay, so then I'll take it like this. Okay, so what will be the voltage across VR1 or the upper threshold point? The upper trigger point or threshold point. The upper trigger point or the threshold point, UTP, is given by, that is your VR1, okay, which is I2 into R1. I will just make it little small for you to see the entire thing in a single frame. Okay, so now let me call this current as I2 into R1, right? So I2 into R1 will give you the voltage across the resistance R1, or which itself is the upper threshold point. UTP is equals to I2 into R1. So now V naught, okay, V naught is the voltage across R2. It is understandable because it is a virtual ground. So V naught is nothing but it is the voltage across R2. I have already marked it here, right? So now the current through R2, the current through R2 is obviously equal to I2, right? So there may be a small bias current. So most of the current will flow through the load here. So this is I2. The current through R2 is equals to I2, or your I2 is equals to, I am taking the modulus because it otherwise would have been in the opposite direction, modulus of V naught divided by R2. Okay, so now here I have written VR1. Okay, you can see here VR1 is equals to I2 into R1. So my I2 is V naught by R2. So therefore I can write here as UTP is equals to V naught into R1 divided by R2. My UTP is V naught into R1 divided by R2. Okay, so this is a very important point to be noted here, right? So now when the output switches to positive saturation, that is here, this point, okay, when the output switches to the positive saturation, the voltage at the non-inverting terminal is now more positive, correct or not? So when V naught is equals to plus V naught sat, right? So at non-inverting terminal voltage at non-inverting terminal is positive. This makes the V naught to remain at, it makes V naught to remain at plus V naught sat. It makes V naught to remain at plus V naught sat. So the output will remain at plus V naught sat, right, as long as this particular condition holds good. That is, the voltage at the non-inverting terminal is more positive with respect to the inverting terminal. Now, to switch again, to switch again to minus V naught sat from plus V naught sat. So what you are supposed to do now, if you want to bring the output again from plus V naught sat to minus V naught sat, you have to bring down, okay, you have to bring down this voltage below the ground level, correct or not, right? So the input has to be brought below ground level. Below ground level in the sense it should become more negative. So this is possible only when your input comes here. This is the UTP and this is the LTP. So your LTP now also would have the similar equation what you had for UTP. This is R1 divided by R2, right? And of course I have to put it in the modulus here, right? So your LTP is again V naught into R1 divided by R2 as long as its magnitude is concerned, right? So this is how your output will again remain at this minus V naught sat. Then if at all you want to bring it above, if you want to bring it to plus V naught sat, then again you have to increase the input above the upper threshold voltage. So between the upper threshold voltage or the upper trigger voltage and lower trigger voltage, the output will keep switching between plus V naught sat and minus V naught sat here, right? So this is how you have the working of non-inverting Schmitt trigger circuit, right? In physical look, it is very much similar to your inverting amplifier, but only thing is that the input terminals are changed. This is how you can remember the two circuits, right? The non-inverting Schmitt trigger and inverting amplifier, right? So you have got a small design aspect here, right? It is very simple as long as the design is concerned. So you have I2 100 times IB max, very common expression. I2 is 100 times IB max, and then R1 is equals to triggering voltage divided by I2, and R2 will be simply the magnitude of the modulus of output voltage divided by I2. This is as simple as this. Simple design. All of you are listening to me?
Yes, sir.
Okay.
Yes, sir.
Right. Right.
Yes, sir.
Only very few are replying, and all are very, known voices only. I can understand who are all replying by looking at, I mean, listening to your voice. I expect all of you to be very interactive, right? Please do not ignore when somebody starts teaching. It appears very simple. When you start drawing the circuit, then all the problems will start coming. So please take the things very seriously. Now let us look into one simple example here, right? Using bipolar op amp, using bipolar op amp, using bipolar op amp, design a non-inverting Schmitt trigger circuit. ST stands for Schmitt trigger, to have to have the output to trigger at plus or minus 0.5 volts, output to trigger at plus or minus zero point 0.5 volts, and to produce an output voltage approximately equal to plus or minus 14 volts. Here there is very one important message here in this problem: approximately equal to plus or minus 14 volts. This is the simple problem. Again, you have to draw the circuit. Without the circuit, your design becomes incomplete, which I have been telling since beginning. So this will be minus, this will be plus, this is V in, this is R1, and this is R2, and this is V naught. That's all. This is plus VCC, this is minus VEE. This is what is the circuit. If you are asked, you have to draw the waveforms as well. Okay. So now, anyway, we can have a rough waveform drawn here. Okay. So now here you have 0.5 volts. Here also you have 0.5 volts. So this will be your one point, this will be your another point. So you can draw the output waveform also. So more you practice, better for you in drawing these things. It will be something like this, V naught. This is your V in, right? You please draw these things very properly with the help of scale and pencil. Even in the examination also these things are required. So now using bipolar op amp, so let us take IC741, because nothing has been mentioned which bipolar op amp you have to choose. So once I take the value of IC741, my IB max, quickly, what is the value of IB max for IC741?
500 nanoamperes.
500
500
nanoamperes.
nanoamperes.
Praveen Kumar, yes.
500.
Okay, good. So you have your I2 100 times IB max, so it becomes 50 microampere. So this we have seen several times. Correct or not?
Yes, sir.
Okay. So now since your V naught is plus or minus 14 volt, this implies your VCC is equal to, what is VCC equal to? I did not listen.
13 volts. 15
13,
volts, sir.
15. Chaitra, it is 15. Because your V0 is VCC
Okay,
minus
sir.
1, right? So this VCC should be V0 plus 1, right? So therefore it is 15 volts, plus 15 volts, and VEE is minus 15 volts. This is one thing. Approximately means there is no hard and fast rule that every time your saturation voltage should be 1 volt less than the supply voltage, right? It is a thumb rule, it is taken, right? Generally, assuming that the internal drops are about 1 volt, right? So whatever the VCC you have, less than 1 of that VCC will be the saturation voltage plus V naught set, and minus V naught set will be minus VEE plus 1. So that is the reason why it is given as approximately, not necessary that it should be equal. That point you should always keep. Okay, so then the other two values are very simple now. So your R1 will be, trigger voltage is 0.5 volt, and your I2 is 50 microampere. Please calculate the value of R1. R2 is your V0 divided by I2. V0 is 14 volts, I2 is 50 microampere. These two values you should,
R1 equal to 10k ohms.
10 kilo ohm,
Yes, sir.
R2
280 kilo ohm.
280 kilo ohm, right? So this is 280k, this is 10k, and this is minus 15 volt, this is plus 15. This is a very simple example what we can have in our non inverting Schmitt trigger circuit, and as usual we will be having the other aspects what we have seen for the inverting Schmitt trigger circuit as well. What is that? Can you tell me? Can you recall what other circuitry we had seen in the Schmitt trigger circuit, which is the inverting type? Now in this case we have the UTP equal to LTP. Am I right? So now if your system requirement is to have different, or the LTP 0, only UTP present, or LTP present and UTP 0, that's what we call it as adjusting the trigger point, right? Adjusting the trigger point. Adjusting the trigger point, right? So how would you do it? Let me do it for one case. Probably after having seen how do we adjust the trigger points for the inverting amplifier, so probably non-inverting amplifier also should not be a problem for us. So now you can understand when I have drawn it like this, what is my intention here, correct or not? So this is my V in, R1, R2 minus, sorry, this is plus, this is minus, plus VCC minus VEE, and this is V0. Please try to draw this circuit as many times as possible. Do not get bored. That makes you a lot of good practice. So now what should I include here?
Diode.
Yes, I have to include a diode. These are very simple. So the diode D is connected in series with R2. So now what happens? The analysis is very important here. When the output is positive, right? When the output is positive, what happens to the diode? When this is at plus V0 set, say the diode will be reverse biased. Am I right? This is plus.
Yes, sir.
Yeah. When V naught is equals to plus V naught sat, D is reverse biased. The diode is reverse biased. So obviously, if the input voltage is 0, then the voltage at the non-inverting terminal here, right? So that is also 0. So obviously, your LTP will be 0, right? So your LTP equal to 0 volt. This you can clearly understand. We have already seen it from the point of view of inverting Schmitt trigger circuit, right? So when the input is 0, your voltage here at the non-inverting terminal is 0, so obviously your LTP is 0, right? So now if the voltage goes just below the ground level, right, if V in goes below the ground level, please understand we are trying to see the situation in the negative half cycle here, because the diode connection, right, is concerned with the negative half cycle. Okay, so if the V in goes below ground level, right, so the output V naught switches from so plus V naught sat to minus V naught sat, correct? Or the output will switch from plus V naught set to minus V naught set. That is the reason why I have started from this particular condition, right? If the input goes below the ground level, your V naught will switch from plus V naught set to minus V naught set. Obviously, now what happens to the diode? Diode will become
Forward bias.
forward biased, correct? The diode will become forward biased. So obviously now once the diode becomes forward biased, you have the equation for UTP, which will be slightly changing now because of the voltage drop across the diode, right? So this is R1 divided by R2. So earlier we had only V naught into R1 divided by R2. So now the voltage drop across the diode, which is Vf, that also comes into picture in many cases, right? So you may ignore that also. Otherwise, you will get the same equation what we have got in our previous case. So this is basically to have the LTP 0, right? So UTP is okay, LTP is 0. Please draw the input output waveforms on your own, okay? And if the diode is reversed, second case, when the diode direction is reversed, right, do the analysis. So you should be able to do on your own. Am I right or not? Can you do these things? Can you do these things?
Yes, sir.
Okay,
Yes, sir.
right. Now, with these things, okay, let me take up an example. Let me see how we will be able to solve this example. So this is adjusting the trigger point, and when the diode is connected like this, when the diode is connected in the other direction, what exactly happens, how your LTP becomes 0, how your UTP becomes 0, and how would you get the change in the waveform, all those things probably you should be able to understand, right? So now with that as the reference, let me take one simple example here, right? Design a non-inverting Schmitt trigger circuit. Design a non-inverting Schmitt trigger circuit to have UTP equals to plus 3 volts and LTP equal to minus 5 volts. Please see here. Use IC 741 with supply voltage of plus or minus 15 volts. Very important example. Many things I have not repeated here. Probably in this problem I will have to recall what we have done for similar problems in inverting Schmitt trigger circuit in our earlier classes. So can you start drawing the circuit now? See here, I have to take care of both UTP as well as LTP, which are different. Okay, which are different. So that's why I have to have a circuit. Here I will have R1. Then can you tell me now what should I have here? Should I not have two diodes in anti-parallel? Yes or no?
Yes, sir.
Okay. I'm audible, right? Okay, fine. So now this becomes your circuit. So this is plus, this is minus. It is already given that this is 15 volt and this is minus 15 volts and this is your V0. So now I will write this as R3 and this as R2. This will be R1. So now when this is R3, here the current will be I3 and this current will be I2. This diode is say D1. Let me write this as D1 and this as D2. This completes the circuit now. This is my V in. Now all of you first please draw the waveform. That is very important here. Please draw the waveform and you can assume any input voltage V in, which should be probably much greater than your 5 volts, because your LTP itself is minus 5 volts, right? So can you draw the input and output? So this I will take it something like this. So let me draw the input signal something like this. V in T. UTP is 3 volts, so therefore I will have to have UTP which is equals to 3 volts. So your LTP is minus 5 volt, so therefore let me have it little bigger, minus 5 volts. So now this will be my reference for drawing the input and output. Yes. I will have the output now, so let us keep it like this. This will be my output, switching between minus V0 sat to plus V0 sat. Definitely you would be able to see the change in the pulse widths. plus V naught sat. You have to write what exactly is plus V naught sat and minus V naught sat. Since it is 15, so this will be plus 14 volts. This will be minus 14 volts. This becomes your I/O waveform. Please see the difference in the values of UTP and LTP. Okay, so now had this branch not been there, that is D2 and R3, so probably you would have got your LTP 0, right? So now in order to have your LTP equal to minus 5 volts, so this is required, and your I3 is going to be decided by that you have to always keep at the back of your mind, right? So now how do you take the value of I2? Earlier we had taken I2 is 100 times IB max. Am I right? All of you are listening to me?
Yes,
Yeah,
sir.
I2 equal to 100 times
Yes,
IB
sir.
max. So as long as your IC741 is concerned, so definitely you would have taken I2 equal to 50 microampere had there not been the diode. Correct or not? If the diode would not have been present there, then you would have straight away taken the value of I2 equal to 50 microampere. But now since the diode is present, you should have minimum forward current for the diode. So therefore, whenever the diode comes in the forward path, so your I2 should not be taken based on 100 times IB max. It is the minimum diode forward current. Okay, so let us say it is about I think we had taken it as 500 microampere in our previous discussions, if I remember correctly, right? You take the same value 500 microampere, right? So now once if you take I2 equals to 500 microampere, so you have UTP is equals to 3 volts. So obviously you should be able to get the value of R1, which is equals to VR1 divided by I2. So VR1 itself is your UTP. So therefore it is 3 divided by 500 microampere. Can somebody tell me the value of R1? 3, 500, 5, 6, I think it comes in 6 kilo ohm.
6 kilo.
6 kilo ohm? Yeah.
6 kilo ohm, sir.
6 kilo ohm, fine. R1 is equals to 6 kilo ohm. And obviously your R2 is equals to, we have already written that, V0 minus Vf, okay, into, sorry, R2 divided by I2, So V0 is plus 14 minus 0.7. You can take Vf is equals to 0.7 volts, right? Divided by 500 microampere. Can you?
26.6 kilo ohm. 26.6 kilo.
26.6 kilo ohm. This is the value of R2. So R1 and R2 are fixed now. But now we are interested in the LTP part. UTP part is very clear to us, right? Because if you don't consider this part, your circuit would have been the same what we have discussed earlier. But now we have to look into the LTP part, right? So for LTP which is equals to minus 5 volt, okay? So your VR1 is also equal to LTP. Now your VR1 has to get changed. VR1 has to get changed. So now how would you change the VR1 value? It is only by virtue of I3, correct or not? In the earlier case, VR1 is taken by virtue of I2. Now your VR1 has to be taken by virtue of I3. That is the only reason or only way how you change the value of VR1. So your I3 has to come into picture now, right? So therefore your I3 will be equal to VR1 divided by R1. So now your VR1 is 5 volt. So I am taking the modulus of this. Your R1 is calculated as 6 kilo ohm. So your I3 will be 5 divided by 6 kilo ohm. 5 by 6.
833.3.
833.3 unit. Can you tell me? Microampere?
Microampere.
Yes, it should be in microampere only. So see here now, I2 is different and I3 is different. Obviously they are supposed to be different only, right? And now this I3 is definitely more than 500 microampere. So that caters to the requirement of your diode also, right? So that part is already taken care of. Otherwise you have to look into that particular issue also. Suppose if your I3 is coming less than 500 microampere, then you probably have to assume the value of I3 also. That time it may not be possible to meet the requirement of LTP equal to -5, right? Anyway, in this problem we are not getting that particular issue. So now from this you can calculate the value of R3. You can easily calculate the value of R3. R3 is nothing but V naught. Look at the diagram. R3 is nothing but V naught minus VF, the voltage drop across the diode, divided by I3, right? So you can write R3 is equals to V naught minus VF divided by I3. So this is 14 minus 0.7. It will remain minus 0.7 only because the diode direction is reversed now. It is not for the same diode, right? Please don't do those kind of mistakes. So divided by 833.3 microampere. R3 is V naught minus VF divided by I3. Can somebody tell me the value of R3 now?
15.9 kilo ohm.
15.9 kilo ohm. 15.9 kilo ohm. So R3 is 15.9 kilo ohm. Now because of this, okay, your I3 will be different, and the UTP and LTP, since they are different, obviously they are obtained from I2 and I3. So this is how you have to solve this particular problem. I hope everyone has understood this. Yes?
Yes, sir.